All right, physics reaction video number 45. This is exciting for two reasons. First, John submitted this video through the Physics Teachers Are Awesome form, meaning that he purposely wants me to react to it and is willing to then hopefully get together with a couple other people that I do reactions to and to debrief. So that's really exciting. And then the second reason is John is actually a former student of mine. He did the Master's of Arts in Teaching license program at my school, and so I had to take, of course, some physics courses. And I was really, really happy to have him in class because he brought a different sort of worldview and experience set, and so it was really fun. And of course, I was also really excited to visit John's class, I think last May or June or something, so I got to see sort of his students. So you can see what he's written here. This is a demo of Castle Activity 5.2. That's an electronics set demonstrating transient processes. Following this video, students should be able to record observations and make conclusions. So that's pretty cool. So let's see how it goes. Let's hope this works. Back this up and hit go.
All right, what we're going to do is activity 5.2, which involves this setup right here. So what do we have? We've got a battery connected to a long bulb, which is in parallel with a capacitor. And then we've got a wire, which is currently not connected, but will be momentarily, to a round bulb. And then the round bulb's connected back to the battery.
So I like this setup. We can sort of see really well everything. Can't quite make out all of the wires here, but it was cool how he used his hand. This is 5.2, he said. So he seems to have a really good understanding of the framing of the camera. From a focus perspective, this taller thing looks a little bit out of focus. The grain of the wood looks quite well in focus. So let's keep an eye out when his hands are in the way if the focus gets bad. But this is really interesting. He said, oh, we got a battery. Here's the long bulb. Here's the capacitor. Here's the other bulb. And so do we need to worry about students being clear how the connections work? It's really interesting. It looks like it's only using 3 D cells instead of 4. And so it's cool how he's bypassing, right? You're clipping on the spring here instead of clipping on the outer tab here. That's very, very cool. So you have to be able to choose just how much voltage you want. So this is 1.5 times 3. So this is 4.5 volts here right now. And so he said long bulb and round bulb. So I guess these are 2 different types of bulbs. So that's pretty cool. Let's see, and a big honking capacitor here. So I wonder. So what I found with the gigantic capacitance capacitors, meaning in the range of a farad, right? Normally instead of micro or nano, they have super cool properties, except that they can have sometimes some internal resistance. They can have some impedance, right? So sometimes they don't seem to work exactly like you would expect a normal capacitor to.
So a wire A, that connects from the battery to the long bulb. Wire B connects the long to the round. And then wire C connects the round bulb back to the battery.
Cool.
All right. So what we're going to do here is I want you to focus on what happens initially when I hook up the circuit, when I connect wire B, okay? What happens to the brightness of each bulb, and how does that change as we reach a steady state? All right, and I'm going to try that one more time.
So what I think I saw was this one light up and stay lit and this one flashing. So let me think about this. So this is battery, a light bulb and a capacitor in parallel, and then another resistor in series. Now see, I'm craving to just like write it down and draw it as a circuit. So I'm really intrigued by that. But I do love this sort of experimental work. Like, wait a minute, why do these 2 bulbs react differently? Though, honestly, the fact that there are 2 different types of bulbs, maybe that's confusing me. So I wonder if he'll like swap it and show, okay, well, let's just swap the bulbs and see it that way. So let me think. So if I've got batteries, mentally I have to draw it, resistor and capacitor, and then battery, and then switch. We throw the switch. Eventually that capacitor is just going to seem like an open circuit. And basically, I guess it'll charge up, right? Yeah. And then it seems like both light bulbs should be lit unless they're very different light bulbs. Let's check it out. Just back them up a little bit.
One more time. And what you should have seen, in case it was not clear, was that the round bulb came on initially, and then pretty quickly turned off, while the long bulb was coming on, and that was lighting up a little slower. So hopefully you saw that. If not, you can rewatch this. Okay, so now the next thing that the lab has us do is check the deflection. So I'm going to grab a compass so we can do that.
Oh, cool.
Now, a lot of you were hypothesizing yesterday that the deflection of each wire should be about the same. So let's see if this actually bears out.
Cool.
So let me first do wire C.
So a couple of things. So love the compass technique, right? It's not overly quantitative, but certainly you can say who's bigger, who's smaller. And so he's going to put the wire right on top of that, and we'll see the compass go whing. That's really, really cool. The second thing is I love connecting to the students and what they said yesterday. Like, yesterday you said this, or you expected that. I think that's super, super useful for students to hear. I'm still confused. So I got to draw this out. So it's so interesting, right? So you're witnessing what it feels like to me to watch this. So I'm going to draw a little battery, and I'll show you what I'm drawing here in a second. I think this is what he has set up. So I'll hold that up to the camera. I think that's what he has set up. Battery on this side, and resistor and capacitor, and then resistor. So when I close the switch, we know that eventually the capacitor is going to be charged. So I like to jump to the end result. We know that eventually the capacitor is going to be charged. So if the capacitor is charged, it'll basically it'll treat like an open circuit. So then I would have expected in the long run both light bulbs to light up. Now at the very, very beginning, in the transient part, there'd be a flat, so at the very beginning, there would be an opportunity for the current to flow rapidly through the capacitor and flash that other light bulb, but I would expect that other light bulb to stay lit, so I'm trying to understand why it wouldn't. The capacitor gets charged. Does it drive the current to zero? So these are the kinds of things, right? Now I could sit here and work it all out and figure it all out, but these are the kinds of things that I'm thinking about. And for others to think about, okay, well, what would I want my students to be doing? But I love the fact, okay, let's measure it and take a look. So let's see how this goes.
Let's make sure we can see that. See it? Okay, there we go. There's a little bit. So it's not moving much. It looks like it's moving about 10 degrees.
Love that.
Let's see what happens on wire B.
So wire B should do the same as wire A or wire C.
It's the. I mean, I'm sure you can see.
Yep.
Hopefully, you're seeing it.
Love that.
It's about the same, about 10 degrees, and then wire A. Let's see what happens here.
I love the editing. You can tell that some editing got done.
And there we go. It's about the same, about the 10 degrees. Okay. So what I want you to do from this, based on, so in the lab, based on your observation, write down what we saw, both in terms of deflection and brightness. And then from there, what you should be able to do is make some conclusions about the pressure differences and the flow rates in the initial state.
So pressure differences in flow rate. So he's doing a plumbing analogy like directly. He's not even using the electrical word. So pressure, voltage, flow rate, current, right? That's super, super cool. Though I've noticed, right, that some people don't understand plumbing. And so to use the plumbing analogy sometimes just goes over the students' heads, and they're like, well, that's not what my book says. My book has this weird word called voltage. So that's really, really cool. Just let him finish up here.
And then the final steady state.
So this was a really really interesting scenario, right? So you got me like thinking, hang on a second, right? I mean, I teach these kinds of things all the time, and I'm still a little bit confused. And I know, I have the confidence that once I sit down and scratch my head a little bit, I'm going to be like, oh yeah, of course, right? And so that confusion that I had didn't impact my ability to really witness what was happening. Now, I would love to swap the bulbs and see how, if you swap the bulbs, how things change, because I'll be honest, I'm still stuck on what is very likely a wrong conclusion. You're all probably laughing at me, but I have a sneaky suspicion that if you swap the bulbs, there'll be a flash on this one, and then it'll stay lit. I think. So, but so cool, right? In these virtual times to show something, to do the deflection with the compass, I could see that pretty well. That was awesome. I think I tend to agree that all three A, B, and C wires had seemingly the same deflection, and surely he has some other videos showing much larger deflections. Also note, but with the exception of the capacitor, this stuff is really cheap, right? So you could certainly ship the stuff to your students or have your students buy it and somehow reimburse them or something. At the college level, we just call it a lab fee. The capacitor is tough. I asked some of you guys, have you solved that problem? But very cool. So thanks, John, for submitting this, and hopefully John and I will be able to talk some more about it. So all right, everybody, have a great day, and remember, physics teachers are awesome.